right, next we're going to look at an example using, oh wow, I just moved the whole screen, sorry, using the theorem. And so we're going to think about an initial value problem where we have du dx is equal to x times u over sine of x. And I'm back to using u instead of y because it's the variable we'll see the most. But just everywhere that you saw y before, we're going to be looking at u. The reason y was in the theorem is because it's much more natural for you to think about spaces in the xy plane. But I'm just going to switch back to u because it's what we use the most. And this is going to be an initial value problem. So what we're going to want to have is u of something is equal to something. And for now, I'm going to go with u of 3 is equal to 7. But we're going to have to erase that and kind of think about a couple different ideas just to make sure we fully explore the theorem. So when we had the theorem statement, what I said was going to matter is this df dy and x0, y0. So for us, the f is xu over sine of x. And the df dy is actually going to be df du. So that's going to be the derivative with respect to u of x times u over sine of x. That's just x over sine of x because, you know, we're taking the derivative with respect to u. So x over sine x is basically a constant. And that's what's left over when we take the derivative. And then our x0, y0 is going to be coming from that u of 3 equal to 7. So our x0 is equal to 3, and our u0, which is what we called y before, is 7. And so let's go back and look at the theorem. So I underlined the things that I said were going to be important. And then the df dy, what we have to do is check that it's continuous over R. Technically, we also have to check that f is continuous over R. But for us, it's going to kind of reduce to the same thing, so it doesn't matter. And then after we know that, as long as it's continuous over this interval, then we know that a unique solution sort of can be found. So what I care about is when is df du equal to x over sine of x continuous? And what's going to happen is x equal to 0 is a problem. Sine of 0 equal to 0 means that df du is equal to 0 over 0, and that's a problem. So since x equals 0 is a problem, but my initial condition x0 equal to 3 came after that, that means that from the theorem, if I look back over here, my x0 starts at 3 and then continues on. So if the only problematic place is x equals 0, then for the entire region I'm thinking about, sort of here is a problem, but I started here at 3, I'm okay over that region. And so I know that there exists this interval where I can find my unique solution, and I'm fine. So the interval of existence would sort of start at 0 and neglect it and go on forever for my x0 equals 3. If instead maybe I had minus 3, then it could go from negative infinity to minus 3. oops, sorry, not to minus 3, to 0. And that would be fine. What's happening is basically that I split the real numbers up according to the region over which the theorem would hold. So split real numbers or possible domain. Basically everything that runs from negative to infinity according to places where the theorem breaks. So for me, x equal to 0 is bad. Possible regions would be minus infinity to 0 or 0 to infinity. Then pick the region that includes your initial condition. So when I had x0 equals 3, I picked 0 to infinity because 3 is inside that interval. And then this tells you an interval over which a unique solution is guaranteed by the theorem. And so I put a star by this topic when we started these videos because I think this is the thing that people struggle with the most in this section. And so you'll have a couple chances to practice that in your web work this week. But hopefully this example sort of gives you a place to start. And next what I'm going to do is sort of wrap up and touch base on what we've discussed. I'm going to make that its own video in case you ever want to look at that just on its own. So I'm going to stop right here. And then in the wrap-up video, you'll get your practice problem for the week.